Hi there. Thanks for joining us on a Q&A edition of Space Nuts. My name is Andrew Dunkley. Coming up, we will be looking at gravity. Is it working backwards and we don't know it? We'll answer that question. Quantum fields, ultramassive black holes, getting up and close and personal with telescopes. Is it possible? And a very interesting surprise at the end from one of our regular sender-inners who's... I'll preempt it by saying, I think it's a joke. You figure it out for yourself. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And it's always good to have the presence of Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Yes, it's good to have your presence too, because without that, I'd be sunk.
Yeah, well, I'd be twiddling my thumbs and you'd be talking to yourself. Yeah. Let's get straight into some questions, and we've got a whole bunch, but some of this might sound familiar because people keep coming back to topics we've discussed and asking questions about questions that we've answered, and that's fine. I mean, it keeps the conversation going, and obviously, people are very interested in a lot of these topics. This first question comes from Carrick. Hello, Space Nuts. Sending this question from Wengari, New Zealand. I hope I pronounced that correctly. I was pondering gravity and dark matter recently and had a thought. We understand gravity as a force that pulls us into objects with mass. However, is it not possible that this attraction force is not there at all and is replaced by a force that is rather pushing us away into objects with mass? My thinking behind this started from the fact that our known universe is expanding at an accelerated rate, and the cause behind this unknown energy or force is dark energy. Even as we experience this on Earth, rather than being attracted towards the centre of our Earth, are we rather repelled by the forces towards Earth? Thanks for taking the time to read this. Carrick. Thanks, Carrick. That turns the whole gravity theory upside down, Fred.
Yeah, it's so... I mean, in a way, it's a legitimate way of looking at gravity. And it goes to something we were talking about in the last episode. If you look at, Einstein's relativity, which is probably the best... Well, it is the best theory of gravity we have. And imagine what a massive body does. We can only illustrate it in two dimensions because we haven't got three-dimensional cartoons for this sort of thing. But it's always the picture of something solid like a planet sitting on a basically a trampoline sheet, which it's bending and pulling down to the middle, so that what you've got is a representation there of the shape of space. And it's the massive object that is causing the distortion of space, and that puts a slope, puts an incline onto the shape of space. So from our experience here on Earth, if we're standing on the planet's surface, the shape of space is slightly different at our head from what it is at our feet.
Could that be demonstrated, and this is just my brain thinking, the same way a ship displaces water? Is that the same kind of effect?
If you've got a ship displacing water, it basically you put the ship in the water and the water moves away, and so that's a sort of static thing. With gravity, what you've got is a bending of the surface. Now, a ship in water doesn't bend the surface; it does for a bit.
Right, I see.
It goes back.
Okay,
but with the space itself, that bending stays there. Space bends in response to matter, no matter what it is. And you could, what Carrick says is correct. You could equally well, given that scenario of the planet sitting on a trampoline and distorting the surface. You could equally well think of that as being something that's pushing you from the outside, because it's effectively the same thing. The bottom line is that space is being distorted by gravity, and we feel that as a pull. But equivalently, we could call it a push from the outside, because it has the same effect. So relativity does sort of, in some ways, lead you to that effect. The bottom line, though, and I guess the focus of the thought trail that Carrick was pursuing there, is that yes, we understand all that and that all works, but dark matter and dark energy are both things on top of that actually affect. They do affect the shape of space in their own different way. But it's not the same as just normal gravity, which is very predictable and very understandable. So I don't think we could use that notion as any kind of vehicle for illuminating what dark matter and dark energy are. That's got to come from the work that's already ongoing, I think.
Okay, so
physics and cosmology.
But his idea does hold a little bit of water in terms of the Earth is, sitting on the trampoline and the trampoline's pushing back.
Yes, that's right. In a way, that's correct. So that anything coming from the outside edge of the trampoline, you roll a marble down it or something. You could equally well say, well, that it's the outside that's pushing the marble in, rather than the gravitational mass that's pulling it in. And it's because relativity tells us that it's the shape of space that has changed.
There you go. All right, there you go, Carrick. You weren't far off the mark. Can't wait to read the scientific paper you're now going to write for us.
Yes, that's right.
Okay, we'll move on. And hello to everyone in New Zealand. Beautiful country. Been there a couple of times. Would go back tomorrow, but not to watch rugby. Now, next question comes from Rennie in California. Rennie writes to us fairly regularly. How do quantum fields behave? Do they interact with each other in any way? Take, for instance, a magnetic field with the Higgs field. You might need to elaborate on that a bit, Fred.
Yeah, so quantum fields are the equivalent of subatomic particles. And this is where, quantum theory gets a bit weird, because you can think of a subatomic particle in two different ways. In fact, three different ways, actually, because you can think of it as a particle, something like a golf ball, just to draw an analogue that would be familiar to you, Andrew. Or you could think of it as a wave, and because particles and waves are equivalent. Or you can think of it as a field, because the field is equivalent. And by a field, I mean kind of what we were just talking about in terms of gravity. That bent or distorted trampoline sheet is a field if it's a representation of space, and it's a field caused by gravity. So Rennie's question is how these fields interact, and some of them certainly do, but a magnetic field probably doesn't interact with a Higgs field. And I'm not a quantum field theorist by any means, as anybody who is listening to this will immediately realise. But magnetism it's the electromagnetic force, the electromagnetic field, and that electromagnetic field, when you turn it into a particle, it is a photon. The photon is the particle equivalent of the electromagnetic field, and a photon does not have a rest mass. It's got a mass, but only because of its energy as it moves. It doesn't have a rest mass. And the Higgs field is what imparts the rest mass to other particles. So my guess is, and it is just a guess here, Andrew, that magnetism does not interact with the Higgs field. But I think some of the other particles would do. The other fundamental particles would interact with one another because their fields do.
Okay, right.
Thanks for that, Rennie.
Yeah, look, he comes up with some real pearls of questions.
Great questions. Yeah,
he puts. You must have a very quick mind, Rennie, to come up with these questions. He puts a lot of thought into them, and some of them are really clever, really clever. Good to hear from you, Rennie. Keep them coming. I know we've got a couple of more in storage that we'll pluck out sooner or later and answer down the track. But good to hear from you as always. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, another regular contributor, and we didn't hear from him too long ago, but he always seems to, like Rennie, come up with a few curveballs for us. It's Rusty in Donnybrook.
Andrew and Fred. Rusty in Donnybrook. Just wondering, would an ultra-massive black hole near the centre of a large void be revealed by its gravitational lensing of distant galaxies?
You kept it short and sweet. Okay. So did you catch that, Fred?
I did, and okay. I've got a short and sweet answer. Yes.
Care to elaborate?
Yeah. So, so everything acts as a gravitational lens, no matter what it is. Including the Earth. There have been ideas proposed of putting a spacecraft at the focus of the gravitational lens represented by the Earth. I can't remember where it is. It's a long way off.
Yeah, I can imagine it would be.
Find a stable point. But any object will distort things behind. The sun, the classic example, and the fact that when the eclipse of 1919 was observed, the stars of the Hyades, which happened to be behind the sun at that time, were distorted in their positions by the gravitational effect of the sun. And so gravitational lensing is a property of all objects. A human would do it if we were in space. So, yeah, a supermassive black hole is going to do it. The issue might well be, though, if the black hole is an active one, that's to say it's gobbling up stuff around it and radiating, it might be quite difficult to see the stuff behind it because we've got, we'd have an accretion disk which is glowing, and as we know from the Event Horizon Telescope, that will be radiating and we'll be able to see the accretion disk. So, yeah, it's something that would happen but might be very difficult to detect.
Okay. All right. Thank you, Rusty, as always. And I'm sure he'll send in more questions because he does. He just does. But he's another one that probably spends a lot of time contemplating these things. We had Rusty on as a special guest some time ago, and we got all these questions out of his system, but then he came up with plenty more. Next question comes from David. If the James Webb telescope can see so far into the past with such great detail, why can't we have a telescope where we can see every grain of sand on the moon? Or do we? Thank you, David. I must confess I've wondered the same thing.
Good. Well, I'm here to tell you why.
I'm guessing there's a reason why not.
There is, and it's all about the ability of a telescope to see detail is something we call in the trade the angular resolution, and it's the angle on the sky that is the finest detail that the telescope can reveal. With the Anglo-Australian telescope here in northwestern New South Wales, the 4-metre Anglo-Australian telescope, 3.9 metres, the one I was astronomer in charge of for a while, that, if you put it in space, would resolve detail on a scale of a 30th of an arc second. Now, an arc second is the angle made by basically a dime or a $1 coin at a distance of 5 kilometres, about 3 miles. It's a tiny angle. The AAT in space could resolve a 30th of that, something like a 30th of an arc second. So the bottom line, however, is that because we're sitting at the bottom of an atmosphere that's quite turbulent, the very best you can do is about 0.9 of an arc second on a really exquisite night. that would be the angle, the minimal angle that you would be able to resolve. Now, the James Webb telescope is a 6.5 meter telescope. It's bigger than our Anglo-Australian telescope, which is 4 meters, I just said, 3.9 meters. And the sensitivity to detail depends linearly, actually, on the diameter of the telescope. So the bigger the telescope, the finer the detail you can see. So with the James Webb telescope, the finest detail it can see is 0.068 of an arc second, a little bit less finer than a tenth of an arc second.
Is that because of its size and the fact that it's not being disrupted by Earth's atmosphere?
That's correct. That's correct. It's 68 milliarc seconds. Is that right? Yes, 0.068. It's quite a bit less than a tenth, actually. Anyway, the bottom line is that's the finest detail that the telescope can resolve. You put it anywhere else, and you can point it anywhere in the universe. This is what I'm trying to say, and you will get that same resolution to detail, whether it's distant galaxies, whether it's the planets, whether it's exoplanets. You will get the same fineness of detail. So what happens if you point it to the moon? You get a resolution of 0.068 arc seconds. What does that show you at the distance of the moon? It will show you details on a scale of 126 meters. That's the finest thing that you could see on the moon with the Webb telescope. And it's quite big. It's not grains of sand. It's 126 meters. It's a big object. And that's because the moon's a long way away, 384,000 kilometers. So,
okay. Do you think that the day may come where they'll build a bigger and better telescope that may be capable of much more detail? I'm going to envisage the answer is yes.
Yes. So that we already have that on the stocks. The 39.3 meter diameter ELT, the extremely large telescope being built at Cerro Amazonas in Chile. Now, that telescope is at the bottom of the atmosphere, so it suffers from that, but it's got a very, very sophisticated system of adaptive optics on board that will give it 20 times the detail sensitivity of the Hubble telescope.
Wow.
Remember, the Hubble's not the James Webb, but it's smaller. So it's a very fine resolution machine. We still will only be seeing detail, on the scale of tens of meters on the moon. Imagine seeing grains of sand. You probably need a telescope bigger than the Earth. I haven't worked out what it is. And it's actually a lot easier just to send a spacecraft with a camera on it. And that's
Exactly.
how we've seen images of all the Apollo landing sites because of Lunar Reconnaissance Orbiter, which is photographing it from 30 or 50 kilometers above the surface.
Yeah.
So, yeah.
I was sort of harking back to the 60s and the early 70s with the moon missions after they were all complete. Of course, 3 gazillion books were released, and I got one that was aimed more at younger people. And even though back then we only had black and white television, yes, kids, it's true, we only had black and white television, and the pictures were quite fuzzy. The book was mind-blowingly beautiful. The images, as I recall from that book, were so high definition compared to what we could see on TV. I was absolutely blown away by it.
Yeah.
So even then, the cameras that they had on the moon were quite brilliant. But when they go back and start walking around up there again, I can't imagine what the pictures are going to be like with modern day equipment. It's going to be very exciting. And even the pictures coming back from Mars are so high def these days.
That's right. Yeah, they're fantastic. I'm just going to revisit something I said, Andrew.
Yeah.
Which was about the Anglo-Australian telescope being able to resolve a 30th of an arc second. That is assuming the mirror is absolutely perfect with no flaws on it. So in reality, it will be slightly worse than that in space. And that's why the figure that I mentioned for the James Webb telescope, 0.068, is sort of, sounds as though it was worse than the Anglo-Australian telescope. It's not. It's much better. But that takes into account the imperfections in the mirror as well. Whereas the value that I quoted for the AATs is if the mirror was perfect, if it was an absolutely perfect mirror. And the only thing that was limiting its ability to see detail was the theory of diffraction, which is what we're up against.
Yeah. And
just in case anybody was listening carefully and said, wait a minute, he just said something else. That's why.
I can't imagine what the budget is at a telescope like the Anglo-Australian for Windex. I mean, that must cost a fortune.
The Anglo-Australian telescope mirror is cleaned once a year when the aluminium surface is removed and it's recoated.
Right.
So it's never cleaned with chemicals. Some observatories avoid doing that by using carbon dioxide snow. Blow solid carbon dioxide across the mirror, and that takes away some of the dust. We don't do that at the Anglo-Australian. We take the surface away and recoat it. But just down the road from the Anglo-Australian telescope is the United Kingdom Schmidt telescope, which I was also astronomer in charge of.
Yep.
And that has a 1.2 metre diameter lens at the front, not a mirror. It does have a mirror in it, but the main thing that gets dirty is a lens. And guess what? We used to clean it with Windex.
So you ask a dumb question, you get a great answer.
Sometimes that's right.
Sometimes it works. Oh, I was joking. Anyway, that's good. That was good to know. Yeah. Oh, well. So, no, it can't work, David. It's just a bit beyond our capability, and as Fred said.
It's physics that dictates it.
Yeah. And if you wanted to build one capable of that, you might as well build a whole planet.
Yeah.
Although that worked for Darth Vader. But, all right. Thanks, David. Thanks for the question. One final thing. It's not a question. It's one of our regular sender-inners who shall remain nameless because he'll tell us who he is anyway. This is a kind of, well, he's going to eventually tell a joke. But you're going to have to, because he bleeps part of it out, you're going to have to use your brain to figure out the punchline. Some people may already have heard this one. I love it. Here's Martin.
Hello, Space Nuts. Martin Berman Gorvine here from Potomac, Maryland, USA. Writer extraordinaire in many genres, especially science fiction. And I am currently working on a novel about an obnoxious billionaire called Egon Rusk and his plans to take a starship full of dim-witted celebrities to found a new master race among the stars, and how these plans may or may not come to grief. I don't actually have a question this week. I actually just have a little-known bit of Star Wars trivia. Did you know that George Lucas was originally planning to have Luke Skywalker's home planet, Tatooine, be a satellite of the seventh planet of our solar system? Yes, but he had to move the planet Tatooine to a long, long time ago in a galaxy far, far away because someone pointed out to him that his original plan would have resulted in a double planet called Tatooine your bleep. Okay. That's all the time we have for dad jokes today. Berman Gorvine, over and out. Out.
Oh, Martin. I love that joke, though. I really do. It's very clever. Again, a play on words. It has done the rounds a bit, but it's always worth retelling. Good on you, Martin. If you've got a question for us, please jump on our website and send it in. You can do that by going to spacenutspodcast.com, and then all you need to do is click on the AMA tab at the top, And it's a simple case of just sending us a text question, or if you've got a device with a microphone, you can send us an audio question. As always, don't forget to tell us who you are and where you're from. And we'd love to hear from you, no matter how big, small, or insignificant the question. We'll give it a crack. And sometimes we get very similar questions. So if we don't answer yours, chances are it's because someone else asked something the same. And while you're there, just have a look around. And if you're on social media, don't forget to like us or follow us or subscribe, depending on which platform it is. We're all done, Fred. Thank you, as always.
Thank you, Andrew. Good to talk to you. And we'll catch up again soon, I think.
We will, yes, indeed. Professor Fred Watson, astronomer at large, and Hugh in the studio, who didn't ask us any questions today. It's very disappointing. But I'm sure that'll fix itself down the track. From me, Andrew Dunkley, thanks for your company. We'll catch you again real soon on another episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.